Hey, what's up, everyone? I am back. It's been a crazy 6 months or so. There's been kind of a lot going on in my life, but I am back and I'm making videos again and I am teaching math once again. I missed it and I'm really happy to be teaching calc and pre-calc once again. So this video aims to just give the basics on a few different topics that kind of bridge the gap between calculus one, or actually not calculus one, it kind of bridges the gap between derivatives and integrals. That's what I meant to say. So the main topic of this video is going to be the two fundamental theorems of calculus. Those are the things that not only tell us why integrals are useful to know, why it's good to know how to do integrals, how they're useful, but it also tells us the relationship between derivatives and integrals. They are related, just like many other things are related. There's kind of like an opposite relationship between derivatives and integrals, kind of like how addition and subtraction are opposites and multiplication and division are opposites. So derivatives and integrals both fall into that category. They are opposites. They undo each other. So before we even get into the fundamental theorems, one topic that I want to talk about is the concept of an antiderivative. So by this point, if you're watching this video, I assume that you have a really good grasp of the concept of a derivative, how to take the derivative of a function. So for example, we know that if we want to take the derivative of the function x squared, we're going to use something called the power rule for derivatives. It tells us that we have to multiply the entire thing by this exponent. Our exponent is 2. So we're going to multiply everything by 2. And then we have to subtract 1 from the exponent. So we have 2. We're going to subtract 1 from the exponent. Our result is going to be 2x. That is the derivative of x squared. But what happens if we wanted to go backwards? What if we didn't have x squared to work with and we wanted to figure out the antiderivative of 2x? We're going backwards. We're not taking the derivative. We are taking the antiderivative. So the notation that is most commonly used in math textbooks is going to be this capital F. So capital F is typically understood to be, I meant to make this a lowercase f. Geez, get it together. So lowercase f of x is our function, and the convention that we use to notate an antiderivative would be capital F. So capital F of x is going to be the antiderivative of 2x. So instead of having a function and we're being asked to take the derivative of the function, we're being asked what function has this derivative. So in other words, the derivative of what gives us 2x. So we know from what we just did a couple minutes ago that that function is x squared. The derivative of x squared is 2x. That's what I meant. No, sorry. Can't talk right now. That's how excited I am. So if our function is 2x, the antiderivative of our function is x squared. But we're not quite done yet. I think I forgot something, left something out, accidentally on purpose. So what if we had not just x squared, what if it was x squared plus 2? Well, the derivative of x squared plus 2 is 2x. So that is still correct. What happens if it was x squared plus 3? Well, the derivative of x squared plus 3 is still going to be 2x because the derivative of any number is just 0. But what if we work backwards? What if there was a number here at the very beginning and we don't know what it was? So that's why the antiderivative is actually going to be plus c, because there could have been a number there at the beginning, there might not have been, and if there was, there's no way of knowing what it was unless we were to do an initial value problem, which I'm not going to get into in this video. But generally speaking, in most antiderivative cases, in the simple case like this one right here, we know that there is no way of figuring out what this number was or if there even was one at the beginning. And the reason for that is because the derivative of x squared plus 4 is the same as the derivative of x squared plus 5, which is the same thing as the derivative of x squared plus 10, x squared plus 5,042,000,042, x squared plus pi. It goes on and on like that. So the derivative of x squared plus any number, we don't know what it is or if there even was one to begin with, is 2x. So that's how we do antiderivatives. And I'm going to just tell you right away, if you don't know this already, antiderivatives are much more difficult than I meant to say antiderivatives are much more difficult than derivatives. So derivatives, they can be grindy, they can be tedious, but overall they're not too difficult. We have explicit rules that tell us how to take the derivative of anything. We have power rule, product rule, quotient rule, chain rule, all that happy stuff. We can take the derivative of anything. It might take a long time for complicated functions, but we know for sure that we can take the derivative of anything. We can't say the same thing for an antiderivative. There are some things that just don't have an antiderivative, some things that are not able to be integrated. And an integral depends heavily on being able to take the antiderivative of something. So if we want to take the integral, the definite integral, or the indefinite integral of something, that relies heavily on the concept of an antiderivative. And like I said, there are some things we just can't take the antiderivative of. And I want to give you a quick example real quick, something that I personally think is a little bit interesting, but you might beg to differ. Now, this is a statistics example. I used to teach statistics quite a bit, but it's been a while, and my drawing sucks. Yeah, I know it does. But this is probably one of the most useful applications of the fundamental theorem of calculus and the fact that the definite integral gives us the area under the curve. So what we have here is something in statistics called the normal distribution. It is a bell curve, and it tells us that can't talk again. It tells us the probability of a certain value of x in a random variable being within two boundaries. So between a value of a and between the value of b. And I'm drawing with a mouse right now. I don't have a drawing tablet at the moment, so bear with me. So the definite integral going from a to b of this function right here. So if you ever wanted to graph this on Desmos or a graphing calculator, the function you would want to graph is e to the x squared. This gives you the normal distribution, the bell curve in statistics that tells you the probability of picking a random value between a and b. And this does not have an antiderivative. It's impossible to integrate this by hand. It's impossible to integrate this without use of a computer. You have to use numeric integration to get the answer. So real quick, I don't want to spend too much time on this, but I thought this was interesting. If we start at negative infinity and go up to positive infinity, this actually has an integral value of just 1. So we have negative infinity to positive infinity. And this is called an improper integral. And most people don't explore the concept of an improper integral until calculus 2 or calculus BC if you're in high school. So I'm not going to go over that too much. I just wanted to let you guys know because I thought it was interesting that this actually has a value of 1. And we know that's true because the entire sample space of the normal distribution in statistics is 1. The probability of picking anything between our lower bound and our upper bound, negative infinity to infinity, is going to be 1. You're guaranteed 100% of the time to get something between this value and this value. So you manipulate this one to get this one, which does not have a value of 1. We have clearly defined boundaries. A is our first, and then B is our second. So this tells us, again, the probability of picking a random value between A and B, and it'll be greater than 0, but less than 1. And again, you can't take the antiderivative of this by hand. It does not have a defined antiderivative. In fact, this is called the error function. I don't know why they call it that, but this is the notation convention and the name of this function. So enough of that tangent. I think we understand antiderivatives pretty well, and if you don't, I have some more videos on my channel that explore the topic in a little bit more depth, and I do some pretty interesting examples to help you understand things a little bit more clearly. So definitely go check those out if you have a chance, if you'd like to have a refresher on antiderivatives. So next, we're going to talk about the main part of this video, the 2 fundamental theorems of calculus. So there are 2 of them, like I said, and I just typically notate them as FTCs. We have 2 of them. The first one tells us this. It tells us that the derivative with respect to x of the integral 0 to x squared, or sorry, just 0 to x for now, of f of t dt is equal to f of x. And like I said at the beginning of the video, derivatives and integrals are opposites of each other, just like addition and subtraction. They undo each other, they cancel each other out. So there are a few different things going on in this process. So we have a derivative and we have an integral. We have the derivative of an integral. They cancel each other out. And of course, whenever the integral gets canceled out, so does this differential at the end. dt is our differential with respect to our variable of integration. That also goes away. And what we're left with is not f of t, but f of x. And the reason for that is because we are changing the variable of integration. We start with the function of t, but this operator that we are applying to it right here, this integral, is an operator being applied to our function of t. We are changing the variable of integration based on whatever happens up here. So that's why the answer is not f of t, but f of x. We are changing the variable of integration whenever we apply the first fundamental theorem of calculus. And then we have the second one that tells us the integral from a low endpoint to a high endpoint. And this time we're going to have just one variable. We're going to keep things in terms of x for the entire time. So the integral from a to b of f of x dx is going to be the antiderivative. So I'm going to make this a capital F of x. Capital F of x is going to be the antiderivative of lowercase f of x. And sometimes people put a really long line here to indicate that we are using the same lower and upper bounds as we did in the beginning when we started this integral. This is pretty common. This is what my calculus teacher in high school did. But what I do is I typically just put them right here. This is our starting endpoint, and here, this is our ending endpoint, A and B. So there's no wrong answer. Just do whatever you're most comfortable with. They mean exactly the same thing. So this means that we are going to be doing the function evaluated at our high endpoint minus the exact same antiderivative of the function. I should make that look more like a capital F to make it really clear that this is the antiderivative. So it's going to be f of b minus f of a. And what this really means is it's going to be the antiderivative of our high endpoint minus the antiderivative of our low endpoint. And I'm going to do some examples to illustrate these both to help us have a really good understanding of what's going on here. So if I can do it without messing up too badly, I'm going to move this over to the left side. I was never good at this part of Zoom. Okay, that wasn't too bad. All right. So let's do some examples. Let's talk about the first fundamental theorem first, because it connects the idea of derivatives and integrals together and helps us have a really good understanding of what it really means to integrate a function. So let's say that we want to take the derivative of, let's make this 1 to x. So it doesn't matter what number this is as our low endpoint. It could be 1, could be 0, could be any number at all, and it has no effect on the answer. And the reason for that is because we know that the derivative of a number is always just going to be 0. So the f of b minus f of a is going to be this. So we're applying the second fundamental theorem to the first one. They're kind of tied together in that regard. So capital F of b is going to be capital F of x. Capital F of a is just going to be 0 because the derivative of any number is just 0. So we don't even really need to include that. And that's why it doesn't matter what number this is. It has no effect on the answer. So let's make this an interesting one. Let's say we have 2 cosine of 5t dt. And we want to take the derivative of this integral. We want to take the derivative of everything inside the box. So we know derivatives and integrals cancel each other out. Starting to sound like a broken record here, but that's it. That's what they do to each other. So when we apply that part of the fundamental theorem, we're going to get the function in terms of x. So instead of 2 cosine of 5t, it's going to be 2 cosine of the quantity 5x. We are changing the variable of integration from t to x. And then we don't want to have a plus c on this one because this is a definite integral. So a definite integral is an integral that has an upper bound and a lower bound. If we erase both of them, this is an indefinite integral. An indefinite integral doesn't have boundaries, and we do need to include a plus c for an indefinite integral. But for this one, we are dealing with a definite integral. It has a lower bound, which is 1, an upper bound, which is x. So we do not need the plus c for that. And I'll be exploring that a little bit later on. either in this video or in another video in the future. So that's how we do it. Let's do one more example of this. Let's make this the integral going from, I don't know, 3. And then let's make the upper one a little bit different. Let's make it square root of x. And then let's say we have the natural log of 3 plus, let's just call it 3 plus u du. And u is just another variable in this case. Sometimes u is the notation we use to notate another function, kind of like f of x and g of x indicate functions. U does something really similar, as you'll know when we do u substitution later on, when we dive deeper into integrals. But in this case, u is just going to be an ordinary single variable, just like x, just like t. We're going to treat it as such. So this one is going to be really similar to what we have above. So the derivative and the integral cancel each other out, and we change the variable of integration to something else. It's not going to be u this time. So last time we changed the variable of integration to x. In this one, we're going to be changing the variable of integration to square root of x. And then we have to do something that we didn't have to do last time. We have to multiply by the derivative of our upper limit of integration. We actually did that last time too. It just wasn't so obvious. So the derivative of x is 1. We always multiply by the derivative of the top function. It's because of the chain rule that we all know and love so well. So the derivative of x is 1, but you don't even really need to put a 1. It doesn't make a difference. It's invisible. But for this one, the square root of x has a derivative that's not equal to just 1. We have a completely different derivative to worry about, and that derivative is 1 over 2 square root of x. That's the derivative of our upper limit of integration. So there you go. This is the final answer for this part of the fundamental theorem. Now let's talk a little bit about the second part. And I miss the days where I could just select a whole bunch of stuff and press the delete key and watch it all vanish, but that doesn't work anymore. So let us try an example for the second fundamental theorem. Let's say we want to take the integral, the definite integral. So we start at 0, we end at 4. That means it's the definite integral. We have a start and an end. So let's say we want to take the definite integral of the function x squared dx. So as with any integral, it doesn't matter if it's definite or indefinite, we always have to take the antiderivative of our function. So the antiderivative of x squared, we are going to approach this the same way we approach the antiderivative at the very beginning. So I'm going to do this off to the side real quick. So when we took the derivative, we did the power rule, which told us that we first had to multiply the entire thing by the exponent, which in this case is 2. And then the last thing we had to do is subtract 1 from the power. So 2 minus 1 is 1. So 2x is the derivative of x squared. But we are actually doing the antiderivative this time. We are going to be working backwards. So we don't know what function we started with, but we're interested in the function that has x squared as its derivative. So we are going to be doing what we did for the derivatives, except we're going to be doing the opposite operations and in reverse order. So we ended last time by subtracting 1 from the exponent. So we're going to do that. We're going to do the opposite of that. We're going to add 1 to the exponent. 2 plus 1 is 3. And then the first part we did when we were taking the derivative of x squared is multiplying the entire thing by the exponent. But when we're doing an antiderivative, we're going to be doing the opposite of that. So instead of multiplying everything by 3, we're actually going to divide everything by 3, giving us either 1/3 times x cubed, or we can also write that as x cubed over 3. So there you have it. That is the antiderivative of x squared. It's x cubed over 3. So you absolutely have to take the antiderivative if you are evaluating this integral using non-numeric methods, if you're just doing this longhand. So we have our lower bound and we have our upper bound. So it's the second part of the fundamental theorem that tells us that our final answer is going to be the antiderivative of b minus the antiderivative of a. So in this case, it'll be the antiderivative of 4 minus the antiderivative of 0. So we're going to plug b in. We're going to plug 4 in for the first part. And then we're going to plug in our low endpoint b, which is 0, to the exact same antiderivative. So this part just goes away completely. It's 0. But for the first part, we have 4 cubed, which is 64. So this is 64 thirds. So why is it useful to know how to do this? Well, like I said before, in that statistics example, that when I went on that really long tangent, the integral tells us the area under the curve. That's what the definite integral tells us. And that's why it's really useful to know how to do this. And you might even be skeptical about why it is important to know how to do the area under the curve, how to find that out. Well, that's because if you want to study science or engineering, medicine, even economics, finding the area under the curve is necessary to figure out the accumulation of change. So I used to study computer science. We used to try to understand how heat flows in a computer. So heat flows through a vector field. So this is another tangent, but I'm not going to make it quite as long as the last one. So a vector field looks like this. At every point, there is a magnitude and a direction that tells us in general how, in which direction whatever we're dealing with is going to be traveling. So with heat flow through a computer, it tells us not only how much heat is flowing through it, but the direction in which it flows. And that's really important to know if you want to figure out like what components are heating up the most and to create airflow systems to keep those things at bay, to keep things at an optimal temperature. Also, if you want to study medicine, we know that everything changes in the human body. Blood flows through our veins, oxygen flows through our lungs, and many other things flow through the bodies as well. So, for example, you want to make sure that you're breathing enough oxygen. So you might have an oxygen flow function, and I know it looks nothing like this, but I'm just doing a quick generalization. So you might be interested in how much oxygen has entered the bloodstream given by this function that represents the amount of oxygen being breathed into the lungs. Breathed? Breathed? I don't know. But the total amount of oxygen can be given by the integral from a to b of whatever our function, our oxygen flow function is in this case. And it's always in terms of time because things are relative only through the notion of time. So that's enough of my other tangent, my second tangent. There might be more, we'll see. But that's why it's important to know how to take the area under the curve. The area under the curve is what gives us these bits of information we need to understand the systems that we're studying. So let's do another example. Or actually, hang on, I wanted to sketch this graph real quick. So we have x squared, and we're going from 0 to 4. We know that it is exclusively positive. The square of any number is going to be a positive integer. So this is my sketch of the function. This is f of x is x squared, and we're going from 0 to 4. So 0 is here, and then 4 is over here. So what we just figured out is that if we were to find the area, all of the shaded area, it is 64 thirds square units. That is the area under the curve going from 0 to 4. So let's do another example that illustrates yet how useful this is. Let's say that we have the integral going from -1 to 1 of this, 1 minus x squared dx. And this is something that we're not able to do in this class. This is something that has what we consider to be a non-elementary antiderivative. To take this antiderivative, if it's even possible, I don't know if it is, I can't remember, but if it is, it takes much more advanced methods than anything we're going to be learning in this class. So we're going to find another way to figure this out. So I'm going to start by graphing it. And remember that this is a really special geometric formula, this function that we're integrating here. It comes from this. It comes from the equation of a circle. So we always have things in terms of x. So we have y equals something. So let's solve for y here. Subtract x squared from both sides, and then take the square root of both sides. And in this case, we can tell that r squared is equal to 1. So our radius is 1. This is a circle with a radius of 1, which looks like this. And again, I'm horrible at drawing. Just pretend like it's a perfect circle and we're all happy. We're going from -1 to 1. So how the heck do we do this without taking the antiderivative? Well, we know that this is going to tell us the area under the curve from -1 to 1. And I'm actually going to do this. I'm actually going to make it a shaded in circle, if I can do so without embarrassing myself too badly. And we're only doing the top half, because remember that if we have the bottom half, it fails the vertical line test, and hence it is not a function. So we're only concerned with this top half. So our objective is to figure out the area under the curve, going from -1 to +1. So the area of a circle we know is pi r squared. But what we have here is actually a semicircle. So the area of a semicircle is going to be half of that. It's going to be half of pi r squared. And we do, in fact, have an explicit radius. We know our radius in this case is 1. So the area will be thus. Pi over 2 is the area, which means that our definite integral is also going to be pi over 2. So earlier I mentioned something about using non-traditional methods, about using numerical methods, to find the value of an still can't talk today. We used a numerical method to solve a definite integral, to evaluate a definite integral. And this is one of those methods. We didn't take the antiderivative. We didn't use the first fundamental theorem of calculus. We used the second one. We used the one that tells us that the area under the curve is equal to all of this stuff. So all we needed to do was use geometry instead of calculus to find that exact same information. We didn't break a sweat, and we got the answer nice and easily. So that's another way to get the same answer. And that's kind of an extension of the topic of a Riemann sum. I'm assuming that if you're watching this video, you have a basic understanding of how a Riemann sum works. Remember that it means we are just approximating the area under a curve by the use of a number of rectangles. So this would be a right Riemann sum, because we're only going as high as the right endpoint, only until the right endpoint reaches our function height. So we know this isn't going to be the exact area. It's a very sloppy approximation, but this is another way we can approximate things using numeric integration. We can even make it more accurate yet. Whoa, what happened there? We can make it more accurate yet by using trapezoids instead of rectangles. So that would look like this, and I'm going to use sharper lines, thicker lines to indicate where we start and end the trapezoids. So that's our first trapezoid. And then we have another one right here. And then another one. And I'm not going to draw all of them. I'm just going to draw enough to illustrate what's really going on here. So notice how the trapezoidal rule gives us a much better approximation than the Riemann sum using only rectangles. So there are quite a few different numerical integration methods. We have left-hand Riemann sum, right-hand Riemann sum, midpoint Riemann sum, which tends to be a lot more accurate than both of those. We have the trapezoidal rule, which is this right here, tends to be much more accurate than all three of those. Something called Simpson's rule. And then we have the process, what we just did is using geometry instead of calculus to get the area. And then you can also use your calculator to get the exact area. If you have a TI-84, it's going to be in the Math 9 menu. It'll take the definite integral of any function. It only works for a definite integral, though. It only gives you the area under the curve. It does not work for an indefinite integral. So that's something to keep in mind. You can also use Wolfram Alpha if you prefer, or Mathway, or any other calculator that you prefer if it's capable of doing those operations. Well, hope you found that useful. And as much as I want to promise you that I'll be making more videos in the near future, I cannot possibly deliver on that promise. I'm actually moving back to Vegas to put more time and effort into my teaching business, my tutoring service that I've been running for a long time. I feel like Vegas just might be a better market for it based on the demographics. And At the moment, like I said, I'm teaching calc and pre-calc. I'm also doing math counts and AMC contests. I am coaching kids to compete in math competitions, and it's super fun and super interesting. So, enough about my interesting life. I hope you found this useful. Hope you guys have a fantastic evening. Enjoy the rest of your day, and I will see you later. Peace.